Hi, Mitch Winger back with another video on data analytics and machine learning. In this video, we'll discuss how to handle unbalanced classes. Hope you enjoy. Okay, let's get started. Let's consider classification models again. In practical classification problems, one class is often rare. In essence, we use classification to find a relatively small number of unusual cases, such as defrauded customers, defective parts, targeting customers who will actually respond. This class distribution is often unbalanced or skewed, often highly so. Evaluation based solely on accuracy does not work. Let's look at an example. If I have a 999 to 1 ratio of negatives to positives, well, I can always predict the negative class. Voila, I've got 99.9% accuracy right there. Now, if we consider some real-world class distributions, such as fraud detection, skews of 10 to the third, 10 to the fourth, or even higher are not all that uncommon. Talk about some accuracy. Let's step back now. Is a model with 80% accuracy always better than a model with 64% accuracy? What about a model with 37% accuracy? As you might guess, the answer is, it depends. We need to know more details about the population. Let's consider two models, Model A and Model B, for a churn example. If we have 1,000 customers and we're going to estimate we have a ratio of 1 to 9 for churn. Let's say we found a data set that has the classes split 50-50 down the middle. Models A and B both correctly classify 80% of this balanced sample. If we look at how they did it, we can see that Model A, or classifier A, has a fair number of false positives. That is, it often falsely predicts that customers will churn. Classifier B makes errors in the opposite direction. It often falsely predicts that customers will not churn. In our data set with the balanced population, both end up with the same 80% accuracy. Now, if we truly expect our population to be split 90-10, we can visualize our model's performance while keeping the rate of false positives in Model A and false negatives in Model B the same. We see that the block representing false positives is now a good deal larger for Model A, while the block of false negatives is much smaller for Model B. Now let's take a numeric look at this same example using confusion matrices. Note the different performances of the models in their respective confusion matrix. Model A and B both achieve that 80% accuracy, although slightly differently. You can look down the diagonals and see 500 and 300 or 300 and 500 for the number of correctly predicted cases, leaving the other 200 as incorrect predictions. So if we calculate the accuracy for the positive cases based on our confusion matrix, we can see that Model A has 100% accuracy for positive cases, while Model B has 60% accuracy for positive cases. For negative cases, we flip the script there. Model A has 60% accuracy, while Model B has 100% accuracy. Now, let's look at our expected distribution of 900-100 in the full population. We can take the predictive accuracy for each case and apply it to our new expected population distribution. Now, with 100 positives, A's 100% accuracy rate puts all cases in the true positive cell, while Model B splits them based on its 60% accuracy rate for positive cases. Likewise, we can allocate the 900 expected negatives using the accuracy rates of each model for negative cases. Model A distributes them 60-40, while Model B places them all in the true negative cell. Now, when we recalculate our accuracy rate for the 900-100 expected imbalanced population, we now have an accuracy rate of 64% for Model A, so its accuracy went down a fair bit, and a whopping 96% accuracy for Model B. So, problem solved. Model B is better, right? Well, as Lee Corso would say, not so fast, my friend. We need to consider the ramifications of each wrong selection. Let's think a minute more about classification accuracy. How much do we care about overall accuracy versus the impact of all the different correct and erroneous decisions? General classification accuracy makes no distinction between false positives and false negatives. In real-world applications, different kinds of errors are going to lead to different consequences. Take a medical diagnosis, for example. If we diagnose that a patient has cancer, even though she doesn't, well, that's a false positive. Now, this is going to be expensive. We're going to conduct some additional tests. It's certainly going to be nerve-wracking to the patient, maybe to the medical care team for a bit, but in general, it's not going to be life-threatening. Eventually, the false positive will be discovered and the patient will be discharged. Now, if we diagnose that a patient does not have cancer, but he does, well, that's a false negative. This is pretty serious, as it may be another year or maybe even more before that patient decides to come in and get tested again. This could have serious ramifications and could be deadly. If you think about it, it's hard to imagine any type of problem where you or your business doesn't really care whether you make a false positive or a false negative error. Therefore, errors should be counted and evaluated separately. In addition, we should estimate costs or benefits for each potential decision and outcome separately. They will very rarely be equal. And we could take this line of thinking beyond classification. How should we measure the accuracy or quality of a regression model? Well, as one example, we could try and predict how much a streaming customer will like a particular movie. Or as an alternative, how much a customer will spend on accessories for our primary product. The typical accuracy measure of regression is the mean squared error, using ordinary least squares in many cases. What does the mean squared error describe? More importantly, how does that relate to the value of the target variable we're interested in? In this case, the number of stars a user will give a movie, or how much they'll spend. For our prediction on stars or spend, is the mean squared error a meaningful metric? How does it calculate into what our prediction is going to be? Or is it just something we learned in a class? The concepts we've just covered, unbalanced classes, unequal costs and benefits, lead us into how we can fully decompose our business problem and put it back together using an expected value framework. We'll discuss that framework in an upcoming video. That's it for this discussion of unbalanced classes and unequal costs and benefits. I hope you found it useful. As always, be sure to check out the other videos in this series.